Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today we're covering a story that should concern every platform engineer. The same IPv6 transition your infrastructure team has been procrastinating on for years is now being weaponized by governments to selectively shut down mobile internet access while leaving desktop users largely untouched. We'll break down the technical mechanics of Iran's January 26 IPv6 Blackout, explain why it disproportionately targets mobile users, and discuss what this means for building resilient infrastructure in an increasingly fragmented internet. But first, let's hit the news.
First up, Kubernetes 1.35 brings a significant refinement to how service account tokens are passed to CSI drivers. The new secrets field option is now in beta. If you maintain a CSI driver that uses service account tokens for authentication with external storage systems, this gives you a much cleaner way to handle that token injection. Previously, the token injection mechanism was somewhat awkward, requiring specific configurations that weren't always intuitive. The new approach follows the principle of least surprise. Storage driver maintainers have been asking for this improvement for a while, and it's good to see it making progress through the beta phase.
Next, HashiCorp published a forward-looking piece on the future of secrets and identity management. Their core thesis is that non-human identity is the future. Think about it. The majority of authentication happening in modern cloud infrastructure isn't humans logging in. It's services authenticating to other services, machines talking to machines. Their argument is that machine-to-machine authentication needs to be automated, seamless, and integrated across platforms and clouds. No more manually rotating credentials, no more hard-coded secrets and configuration files. This aligns with the broader industry push toward workload identity and SPIFFE-based attestation. If you're still managing secrets with manual rotation schedules, it's worth reading their vision for where the industry's heading.
CoreDNS 1.14 is out with a focus on security hardening. The key change is a regex length limit to reduce resource exhaustion risk. If you're running CoreDNS in production, and if you're running Kubernetes, you almost certainly are, this is worth updating to. Resource exhaustion attacks via crafted DNS queries are a real threat vector that doesn't get enough attention. An attacker who can send DNS queries to your resolver could potentially craft regex patterns that consume excessive CPU or memory. The new limits provide a safety valve against these attacks.
The OpenTelemetry community published a fascinating analysis of 10,000 Slack messages to understand adoption challenges. They went through their public Slack channels and categorized the questions people actually ask. The result is a map of where people struggle when implementing OpenTelemetry. Common pain points include understanding the relationship between traces, metrics, and logs, confusion about when to use automatic instrumentation versus manual instrumentation, challenges with context propagation across service boundaries. If you're in the middle of an observability migration, this is worth reading to anticipate and avoid the common pitfalls.
AWS previewed R53 Global Resolver, which uses Anycast to decouple DNS from regional failures. This is a significant resilience improvement that addresses a real concern. Previously, if your R53 region had issues, your DNS resolution could be impacted even if your actual services were running fine in other regions. The new Global Resolver uses Anycast, which means DNS queries get routed to the nearest healthy resolver automatically. This is similar to how Cloudflare and other CDN providers have operated their DNS for years. It's good to see AWS bringing this kind of resilience to R53.
And finally, a sobering reminder about kernel security. A new analysis shows that kernel bugs hide for an average of 2 years before discovery. Some bugs hide for 20 years. The research looked at the life cycle of vulnerabilities from introduction to discovery to patch. The security implications for infrastructure are significant. That stable kernel you've been running unchanged because it works, it likely has undiscovered vulnerabilities. This doesn't mean you should constantly churn kernel versions, but it does mean you should have a strategy for kernel updates and security patching that accounts for the reality that bugs are being discovered in code that's been in production for years.
Now let's dive into today's main topic, Iran went into what observers are calling a digital blackout yesterday, but the technical details reveal something far more sophisticated than a simple internet shutdown. This isn't the crude on-off switch we've seen in previous incidents.
Right. Let me start with what Cloudflare radar detected. Around 15:30 local time in Iran, which is 1200 UTC, they observed a 98.5% drop in Iran's announced IPv6 address space. That's almost complete elimination of IPv6. But here's what makes it interesting. IPv4 connectivity remained largely intact. This wasn't a total blackout, it was protocol-specific targeting.
Before we go deeper, let's make sure everyone understands the relationship between IPv6 and mobile. Why does blocking IPv6 specifically impact mobile users?
Great question. So we need to go back to why IPv6 exists in the first place. The internet runs on IP addresses. IPv4 gives us about 4.3 billion addresses. That sounds like a lot, but consider that there are 8 billion people on Earth, many with multiple devices. Plus, every server, every IoT device, every smart appliance needs an address. We ran out of IPv4 addresses years ago. Exactly. Think about a mobile carrier with 50 million subscribers. Each subscriber has at least one device that needs internet connectivity. With NAT, you're putting thousands of devices behind each public IP. That creates a different scale of problems. Carrier-grade NAT is complex, expensive, and creates bottlenecks. So mobile carriers were some of the earliest adopters of IPv6. They started deploying IPv6 native networks where each device gets its own globally routable IPv6 address. No NAT required.
So when you say Iran blocked IPv6, you're saying they targeted the protocol that mobile carriers depend on.
Exactly. If you look at the network architecture of a typical mobile carrier, especially in the Middle East, where mobile-first adoption has been strong, a significant portion of their traffic is IPv6 native. Desktop users on wired connections, many of which still primarily use IPv4 through their ISP, experienced much less disruption. But mobile users, the people out in the streets protesting, suddenly couldn't reach external services reliably.
The numbers you mentioned were dramatic. IPv6 traffic share dropped from about 12% to 1.8%.
Right, and that 12% baseline tells us something. In Iran, about 12% of total internet traffic was IPv6. After the blocking, it dropped to under 2%. That remaining traffic might be from devices that successfully fell back to IPv4 or from segments of the network that weren't affected, but the majority of mobile IPv6 connectivity was eliminated.
How did they actually implement this technically? Walk us through the BGP mechanics.
Based on what Cloudflare radar shows, it appears Iranian ISPs withdrew their BGP announcements for IPv6 prefixes. Let me explain what that means. BGP, the Border Gateway Protocol, is how networks tell each other what IP addresses they can route to. If I'm an ISP with the IPv6 prefix 2001:DB8:whatever, I announce that prefix to my upstream providers. They announce it to their peers. Within minutes, the entire global internet knows that to reach addresses in that prefix, traffic should be routed toward me.
So withdrawing the announcement means traffic can't find its way to you.
Exactly. When you withdraw a BGP announcement, you're telling the global routing table, I'm no longer reachable at these addresses. The routes age out, typically within minutes, and traffic destined for those addresses has nowhere to go. The packets just get dropped at whatever router realizes there's no valid path.
And Iran did this selectively for IPv6 while keeping IPv4 announcements intact.
Right. That's what makes this sophisticated. The IPv4 prefixes remained announced. Wired internet, business connectivity, banking systems that might be IPv4-centric, those kept working. But the IPv6 prefixes that mobile carriers depend on were withdrawn. It's surgical in a way we haven't seen before at this scale.
This reminds me of yesterday's episode about Venezuela, but the intent seems completely different.
Very different. In Venezuela, we saw a BGP route leak where AS path prepending suggested misconfiguration. Someone's router was probably misconfigured and accidentally leaked routes through the wrong provider. Here, the pattern is the opposite, a clean withdrawal of IPv6 prefixes while maintaining IPv4 suggests deliberate, coordinated action. You don't accidentally withdraw all your IPv6 announcements while keeping IPv4 perfectly intact. That takes planning.
Let's talk about what analysts are calling engineered degradation. Why didn't Iran just shut down the internet entirely?
This is where the calculus has changed. Let's think about what a total internet blackout means for a country. Banking stops, electronic payments stop, business operations that depend on internet connectivity grind to a halt. International commerce is disrupted. The economic damage is enormous and immediate. Governments have learned this lesson the hard way. Myanmar's 2021 shutdown cost the economy billions. Previous Iran shutdowns had similar economic consequences.
So they want to suppress protests without destroying the economy.
Exactly. Engineered degradation lets you target specific use cases. Social media and messaging apps, which protesters use to coordinate, often run over mobile networks. Mobile users are disproportionately affected by IPv6 blocking. Meanwhile, businesses that might use wired connections or have IPv4 primary connectivity can continue operating. It's an attempt to have it both ways, suppress protest coordination while maintaining economic function.
There's another factor you mentioned in our prep, Starlink. There are reportedly thousands of Starlink terminals active in Iran.
This is a crucial part of the story. The presence of satellite internet has fundamentally changed the calculus for authoritarian internet control. In previous shutdowns, the government could create a near-total information vacuum. When the internet goes dark, information stops flowing in and out. But Starlink terminals don't route through Iranian infrastructure. They connect directly to satellites, which connect to ground stations outside the country. Iranian network controls don't touch them.
So even if Iran imposed a total blackout, information would still flow via satellite.
Right. And here's the perverse result. A total blackout might actually be worse for the government than targeted degradation. In a total blackout scenario, the only people who can communicate internationally are those with satellite access. They become the exclusive sources of information. Everyone else is in the dark, but those satellite users are broadcasting what's happening to the outside world. With engineered degradation, more people have some connectivity, but it's harder to coordinate mass action.
Let's pivot to what this means for platform engineers. If I'm running services that have users in regions where this kind of targeting might happen, what should I be thinking about?
First, and most importantly, monitoring. Are you tracking IPv6 availability separately from IPv4? Most observability setups treat connectivity as binary. The service is either up or down. The endpoint is either reachable or not. But we're now seeing scenarios where one protocol is available and another isn't. Your monitoring should distinguish between them.
Can you give me a concrete example of how this would manifest in monitoring?
Sure. Let's say you're running a service with users in the Middle East. You have synthetic monitoring that pings your endpoints from various locations. If you're only checking reachability in general, you might see your Iran synthetic checks reporting 50% success. Looks like intermittent connectivity, right? But what's actually happening is that all your IPv4 probes succeed and all your IPv6 probes fail. That 50% success rate is actually a complete bifurcation by protocol.
So I need IPv4 specific and IPv6 specific health checks?
Exactly. And ideally, you correlate that with what percentage of your real user traffic comes over each protocol. If 90% of your Iranian users are on mobile IPv6, then that 50% synthetic success rate is actually catastrophic for your mobile users specifically.
What about application-level resilience? How do apps typically handle this kind of dual-stack failure?
This is where things get messy. The ideal behavior is defined in RFC 8305, commonly called Happy Eyeballs version 2. The algorithm says when connecting to a destination, you should race IPv6 and IPv4 in parallel with a slight head start for IPv6. Whichever responds first wins. If IPv6 is blocked, you fall back to IPv4 within about 250 milliseconds.
That sounds reasonable. Does it work in practice?
For well-implemented networking stacks, yes, but many apps, especially mobile apps, don't implement happy eyeballs correctly. Some try IPv6 first, wait for a full timeout of 30 seconds or more, then try IPv4. That's a terrible user experience. Other apps might have connection caching that remembers IPv6 worked before and keeps trying it even when it's failing. Some apps might give up entirely after the IPv6 failure without trying IPv4.
So even if IPv4 is available, users might not be able to use your service because the app doesn't fall back properly?
Right, and this is something you can test. Take your mobile app, configure a network environment where IPv6 is blocked, and see what happens. Does your app connect? How long does it take? Does it retry appropriately? Most teams have never tested this.
What about the CDN layer? How do Cloudflare, Fastly, Akamai handle protocol-specific outages?
CDNs are generally well designed for dual stack. They serve content over whichever the client connects with. If a client connects over IPv4, they serve over IPv4. IPv6, they serve over IPv6. That part works, but the problem is the connection between the user's device and the CDN edge. If the user's device can't establish an IPv6 connection and the device doesn't fall back to IPv4 properly, the user never reaches the CDN in the first place.
So the CDN's dual stack support doesn't help if the client-side connection fails.
Exactly. This is fundamentally a client-side problem as much as a server-side one. And you don't control the client side. You can't force users to update their apps. You can't fix their network stack. The best you can do is make sure your own infrastructure handles both protocols correctly and that your monitoring can distinguish between them.
Let's talk about designing infrastructure for this kind of scenario, not from a political perspective, but purely from an availability engineering standpoint.
A few key principles. First, multi-protocol resilience. Make sure your infrastructure genuinely works over both IPv4 and IPv6. Test this explicitly. Don't assume dual stack works just because you have both configured. Create test scenarios where one protocol is unavailable and verify your services remain accessible.
What would that testing look like in practice?
Set up a test environment where you can selectively block IPv6 at the firewall level. Run your full test suite. Make the same requests your mobile clients make. Verify everything works. Then do the same for IPv4 blocking. You might be surprised what breaks. Maybe your health checks only run over IPv4. Maybe a dependency assumes IPv6 is always available. Find these issues before your users do.
You mentioned satellite as a resilience layer. That seems exotic for most organizations.
It's becoming less exotic. Starlink for Business and other satellite providers are becoming viable for redundant connectivity. If your organization has an operations center, network operations center, or any facility that absolutely needs internet connectivity regardless of local conditions, satellite is worth considering. It's not about replacing terrestrial connectivity. It's about having an independent path that doesn't share failure modes with your primary connectivity.
The cost-benefit would depend on how critical that connectivity is.
Right. For most companies, internet outages are inconvenient, but not catastrophic. For organizations in critical infrastructure, finance, healthcare, emergency services, having an independent connectivity path might be worth the cost. And the cost has come down significantly. Starlink Business is not cheap, but it's no longer prohibitively expensive for organizations that genuinely need that resilience.
What about edge compute? How does running at the edge help with this kind of scenario?
Edge compute reduces the number of network hops between users and your services. Every hop is a potential point of control or failure. If your compute runs in a hyperscaler data center in the US, a user in Iran has to traverse their local ISP, international transit providers, and peering connections to reach you. Any of those can be disrupted. If you run edge compute closer to users, fewer of those hops are involved. You're more resilient to upstream blocking.
But edge compute can't help if the edge nodes themselves are in the affected region.
Correct. If your edge is in Tehran, it's subject to Iranian network controls. The benefit of edge is reducing dependency on long network paths that cross national boundaries. For resilience against national-level blocking, you need compute outside the affected region. But for performance and resilience against international transit issues, edge helps. Let's talk about the sovereignty question. Many organizations are focused on data residency and having infrastructure in region for compliance. Does this kind of incident change that calculus? It complicates it significantly. Having infrastructure in region means your data is resident in that jurisdiction, which might satisfy compliance requirements. But it also means your infrastructure is subject to that region's network controls. If you have a data center in Iran to satisfy local data residency requirements, your data is resident, but your users might not be able to reach it if the government decides to block connectivity.
Geographic distribution within a country doesn't help if the blocking is at the national level.
Right. Multi-region within a single country gives you resilience against localized failures, natural disasters, data center outages, but national-level network controls affect all your in-country infrastructure equally. For resilience against this class of event, you need infrastructure outside the affected country, but that might conflict with data residency requirements. There's no perfect answer. It depends on your specific compliance requirements and risk tolerance.
How do you see this trend evolving? Are we going to see more protocol-specific blocking?
I think so. As dual stack becomes universal and more organizations understand the relationship between protocols and use cases, selective blocking becomes more attractive. IPv6 is particularly interesting to block because of the strong correlation with mobile users. But in theory, you could see the inverse, blocking IPv4 to impact legacy systems while preserving mobile connectivity. It depends on what the controlling party is trying to achieve.
The underlying pattern is that any axis of differentiation becomes a potential control point.
Exactly. Protocol, carrier, AS path, geographic routing, anything that distinguishes one class of traffic from another can be used to selectively block or degrade. The lesson for infrastructure design is that homogeneity creates vulnerability. The more your infrastructure relies on a single protocol, path, or provider, the easier it is to disrupt. Diversity is resilience.
Let's wrap up with key takeaways for our audience.
First, IPv6 can be weaponized to target mobile users specifically. This isn't theoretical anymore. It happened yesterday in Iran at massive scale. If your user base is mobile-heavy, especially in regions with authoritarian tendencies, this is a risk you need to understand. Second, your monitoring should track protocols separately. If you're not distinguishing IPv4 and IPv6 availability, you have a blind spot that could mislead you during an incident. Add protocol-specific health checks to your observability stack. Third, satellite internet is emerging as a resilience layer. Starlink and similar services are changing the calculus for both censorship resistance and disaster recovery. Consider whether satellite connectivity makes sense for your critical operations. Fourth, dual stack isn't just about compatibility, it's about resilience. Test your fallback paths explicitly. Understand how your applications and infrastructure behave when one protocol fails. Most organizations have never tested this. Fifth, data residency and availability can conflict. Having infrastructure in a jurisdiction for compliance means being subject to that jurisdiction's network controls. There may be no perfect solution, only trade-offs to manage.
Action items for our listeners?
Add IPv6 specific health checks to your observability stack. Look at your traffic analytics to understand your protocol distribution by region. Test how your services behave when IPv6 is unavailable. Consider whether satellite connectivity makes sense for critical operations. Have conversations with your compliance team about the tension between data residency and availability resilience.
That's the episode for today. Tomorrow we'll be back with more platform engineering insights. Until then, keep building resilient systems.
And remember, in a world where protocols can be weaponized, the best infrastructure is the one that doesn't depend on any single point of control.